Good day, I'm Joseph de Vera, and I will discuss the concepts about LVDT, its parts, and how it works. First, what is an LVDT? LVDT is an acronym for Linear Variable Differential Transformer. It is a common type of electromechanical transducer that can convert the rectilinear motion of an object to which it is coupled mechanically into a corresponding electrical signal. The figure shows the components of a typical LVDT. The transformer's internal structure consists of a primary winding. This primary winding is centered between a pair of identically wound secondary windings. These secondary windings are symmetrically spaced about the primary. The coils are wound on a one-piece hollow form of thermally stable glass-reinforced polymer, encapsulated against moisture, wrapped in a high permeability magnetic shield, and then secured in a cylindrical stainless steel housing. This coil assembly is usually the stationary element of the position sensor. It consists of a primary coil bounded on a hollow cylindrical rod and is connected to an AC source. It also consists of two secondary coils having equal number of turns and is bounded on a hollow cylinder at equal distance on either side of the primary coil. The two secondary coils are connected with each other in series opposition. We see that a movable soft iron core is placed inside a hollow cylinder. The position of this core with respect to the two secondary coils will affect the magnetic coupling between the primary and two secondary coils. Let's now understand how this LVDT works. We see that when an AC source is activated, alternating current starts flowing through the coil, due to which varying magnetic field is produced. Now, when this varying magnetic field interact with the primary coil and the EMF is induced in the two secondary coils, we see that initially the core is placed in such a position that equal EMF gets induced in both the coils, due to which the net EMF of the two secondary coils becomes zero. This position of the core is known as null position. Now, if we move the core towards the right, we see that the flux linking with coil S2 becomes greater than the flux linking with coil S1. As a result, the EMF induced in the coil S2 becomes greater than the EMF induced in coil S1, and the net EMF shows a negative value. Similarly, if we move the core towards the left, we see that the flux linking with coil S1 becomes greater than the flux linking with coil S2. As a result, EMF induced in coil S1 becomes greater than the EMF induced in coil S2, and the net EMF shows a positive value. Thus, LVDT uses the magnitude and polarity of the net EMF induced to measure the displacement of its core from the null position. Here are the advantages of LVDT. First, linearity. The output voltage of this transducer is practically linear for displacements up to 5 mm. A linearity of 0.05% is available in commercial LVDTs. Second, infinite resolution. The change in output voltage is stepless as there are no mechanical elements to change the output voltage in discrete steps. The effective resolution depends more on test equipment than on the transducer. Third, high output. It gives a high output and therefore many a times there is no need for intermediate amplification devices. Fourth, high sensitivity. The transducer possesses high sensitivity as high as 40 volts per millimeter. Fifth, ruggedness. These transducers can usually tolerate a high degrees of shock without any adverse effects. They are simply, and by virtue of being small and light in weight, they are stable and easy to be aligned and maintained. Sixth, less friction. There are no sliding contacts and hence there is less friction and less noise. Seventh, low hysteresis. This transducer shows a low hysteresis and hence repeatability is excellent under all conditions. And lastly, low power consumption. Most of the LVDTs consume a power of less than a watt. However, there are some disadvantages of using LVDTs. First, they are sensitive to stray magnetic fields which may affect the total EMF of the transducer. Second, many a times, the transducer performance is affected by vibrations. Third, the receiving instrument must be selected to operate on AC signals. In other case, a demodulator network must be used if a DC output is required. Fourth, the dynamic response is limited mechanically by the mass of the core and electrically by the frequency of the applied voltage. Frequency of the carrier should be at least 10 times the highest frequency component to be measured. And lastly, temperature affects the performance of the transducer. But when temperature effects are expected to affect the performance, manganese wire may be used instead of copper wire. Unfortunately, manganese has a high resistivity and therefore its use results in loss of sensitivity. The sensitivity with manganese coil may be as low as one-fifth of that with copper coils. Temperature also causes phase shifting effects which may be minimized by using a capacity across one of the secondary windings. That's it. Hope you've understand the concepts behind LVDTs.